Imagine you're building like a massive state-of-the-art skyscraper. You've poured billions of dollars into the steel foundation, the energy-efficient glass, the absolute cutting-edge technology for the elevators.
Right, the whole works.
Exactly. You were literally weeks away from cutting the ribbon. And then you realize the entire structural integrity of this multi-billion-dollar building relies on one highly specific, custom-made titanium screw.
Oh, man.
Right. And the real kicker, the only factory in the world that manufactures that exact screw is owned by your biggest rival.
Wow. So suddenly all that wealth, all that grand architecture, I mean, it means absolutely nothing.
Nothing at all.
You can't finish the project. You can't secure the building. You're just entirely at their mercy, waiting to see if they, feel like selling you that single tiny component.
And that tension, that exact scenario is where the United States finds itself right now. Not with skyscrapers, obviously, but with the entire modern technological landscape. So, welcome to the Deep Dive. Today, we are bringing you inside the hidden, high-stakes battle for the physical building blocks of the modern world.
It is a wild situation.
It really is. And to explore this, we're looking at a pretty fascinating stack of recent sources. We've got official White House fact sheets, press releases from the Department of War, geopolitical analysis from the Modern War Institute, and some really brilliant insights from a tech-focused YouTube interview with innovators on the ground level.
Yeah, and our mission today really is to show you a massive, largely invisible shift that's happening right beneath our feet. I mean, we are moving away from a world where we just assumed the global supply chain would always, magically provide the materials we need.
Right.
Instead, governments and innovators are scrambling and spending billions of dollars to secure what are known as critical minerals.
Okay, let's unpack this. Because to understand the specific, honestly wild technological breakthroughs we're going to talk about later, we first need to kind of zoom out and look at the macro picture.
Yeah, the big policy stuff.
Exactly. We are seeing a monumental policy and financial shift happening at the highest levels of the U.S. government. For instance, the Trump administration recently held this historic roundtable with mining executives. And according to the sources, it was the largest meeting of its kind in over 120 years.
Which is a huge deal.
It is.
All right.
And just a quick note for you listening. We are pulling straight from these political fact sheets and official statements today. We aren't endorsing any specific political viewpoints or administrations here. We're simply and impartially reporting on the stated goals and, honestly, the massive financial shifts that these documents reveal.
And that historical context is crucial, right?
Yeah.
Because it signals a fundamental pivot in how the government views the mining and materials sector. Mining is no longer being treated as just, an economic sector or a commodity market. It's actively being reclassified in the eyes of policymakers as a core component of national defense.
And they are definitely putting serious money behind that reclassification. I mean, the administration announced over $2 billion in new deals for critical mining projects just at that one roundtable.
Where's that roundtable?
Yeah. Looking closely at the White House fact sheet, since January 2025, they have signed or approved 160 minerals deals totaling almost $40 billion.
$40 billion. That's just staggering.
It's massive. And the stated goal here, and President Trump specifically noted this, saying critical minerals are the raw material of American strength, is to aggressively reduce reliance on foreign nations, rebuild domestic capacity, and bolster national security. I mean, they want these materials mined, refined, and made right here in the USA.
And the mechanics of how they're attempting to achieve this are pretty fascinating. They're using Section 232 tariffs, which are these specialized trade tools designed to protect domestic manufacturing by bypassing normal free trade rules.
Bypassing them on national security grounds, right?
Exactly.
Yeah.
But a tariff only works if you actually have an industry to protect, which is why they're simultaneously addressing the human capital side. The Department of Energy is investing $100 million into 14 U.S. mining schools to literally double the number of graduates in this field.
Because you can't just open a plant with nobody to run it.
Right. You simply cannot rebuild an advanced extraction industry if you don't have the geologists and metallurgists to run the facilities.
The specific investments show just how broad this is, too. There's $1.4 billion going to a company called Sila Nanotechnologies for silicon carbon battery anodes.
Which, by the way, holds significantly more energy than traditional graphite.
Exactly. Then the Export-Import Bank is throwing $25 million at Westwater Resources for graphite, another $25 million to Global Advanced Metals for tantalum and niobium.
Which act as essential capacitors for, like, almost all modern electronics.
Right, and $8 million to 5E Advanced Materials for boron. And it gets even more specific. The Department of War dropped an $85.5 million agreement with Strategic Bauxite USA for refractory-grade bauxite.
Oh yeah, bauxite is aluminum ore, but this refractory-grade version resists extreme melting. It's totally mandatory for things like heat shields and turbine engines.
Right. But, okay, I have to push back on this entire premise for a second.
Right.
We have relied on globalized supply chains for decades. I mean, we buy things from overseas, they buy things from us. It is quite literally how the modern economy functions, and, the sky hasn't fallen yet. So why this sudden multi-billion-dollar panic? Is this just political posturing?
Well, it's a really vital question to ask, and the answer basically comes down to a transition in philosophy. We are moving from what supply chain experts call just-in-time manufacturing to just-in-case manufacturing.
Okay.
For decades, the global economy optimized entirely for cost and efficiency. But modern technology, from your EV in the driveway to a missile defense system, relies on an incredibly fragile ecosystem of highly specific materials. What we're seeing now is the implementation of a concept called industrial deterrence.
Industrial deterrence. So like nuclear deterrence, but for factories.
That is the perfect way to look at it. If an adversary knows that a single export ban on one obscure mineral can completely shut down your ability to produce fighter jets or communications networks.
They have immense leverage over your foreign policy.
Exactly. Industrial deterrence means building enough redundancy and domestic capacity that an adversary knows they can't cripple you by simply turning off the tap. You remove the vulnerability so they never try to exploit it in the first place.
Well, to really drive home just how fragile that tap is, we need to kind of move away from those broad billions of dollars and zoom in on a micro problem, a 60-ton problem to be exact. I want to talk about scandium.
Oh, scandium. It is the ultimate case study for this entire geopolitical crisis. It's a specialty metal, and the numbers surrounding its global supply chain are, well, they're almost impossible to believe.
Yeah, looking at the geopolitical analysis from the Modern War Institute, they note that in 2025, the entire global consumption of scandium oxide was just 60 metric tons.
60 tons.
Right. If you are listening to this on your commute, picture a standard railroad boxcar. The entire world supply for a year could easily fit inside that single car. We are talking about a microscopic market compared to, millions of tons of copper or steel.
And despite that tiny volume, you cannot simply swap it out for something else.
Yeah.
It is entirely irreplaceable. When you add a ridiculously small amount of scandium, often less than 1% to aluminum, it fundamentally changes the physical properties of the metal.
This is where I need you to explain the physics a bit, because the sources just sort of say it acts like magic to improve strength, corrosion resistance, and weldability. But how does less than 1% of a metal completely transform a block of aluminum?
Okay, so it comes down to what metallurgists call precipitation hardening. Think of the atomic structure of regular aluminum like a deck of cards. Under extreme stress, those layers of atoms can slip and slide past each other, which is why aluminum bends or tears. But when you add scandium, it forms these tiny, incredibly tough crystalline structures throughout the metal. They act like microscopic rebar, pinning the layers of aluminum together so they cannot slide.
Oh, wow. So it literally locks the atomic structure in place.
It locks it in place natively, and that's why it's so crucial for weldability. Normally, welding aluminum creates intense heat that weakens the surrounding metal, often leading to microscopic cracks.
Right.
But scandium-laced aluminum retains that microscopic rebar even after being melted and cooled, so the weld stays incredibly strong. You get a material that's light enough for aerospace, but strong enough to handle extreme structural stress.
Which explains why it's absolutely mandatory for cutting-edge defense tech. I mean, the F-35 fighter jet program completely relies on aluminum scandium alloys. It's required for hypersonic munitions. It is even used to create a material called scalmalloy, which is this powder specifically designed for 3D printing replacement defense components directly on the battlefield.
Yeah.
You just have to have that strength-to-weight ratio.
If we connect this to the bigger picture, it's not just the military that needs this material. The civilian market is actively exacerbating the bottleneck right now.
Yeah, the civilian tech sector is ravenous for it. Bloom Energy, for example, they make these solid oxide fuel cells, which are basically devices that convert fuel into electricity via a chemical reaction rather than burning it, making them incredibly efficient.
Right.
And they are increasingly being used to power massive AI data centers. Bloom alone consumes about 74% of the global scandium supply.
Just one company.
Just one. On top of that, aluminum scandium nitride films are essential for the piezoelectric components inside 5G and 6G communications networks.
And for anyone unfamiliar, a piezoelectric component is a material that converts electrical signals into physical vibrations, and vice versa. In a 5G phone, these films act as highly precise physical filters. They vibrate at exact frequencies to ensure your phone only catches the 5G signal and ignores all the background noise. Without scandium, that high-frequency filtering becomes incredibly difficult.
So you have the foundational infrastructure of the future civilian economy, AI data centers, next-generation telecommunications actively competing with advanced military fighter jets for the exact same 60 tons of material.
It's a recipe for a crisis.
It is. So if this stuff is so critical, the obvious question is, why don't we just dig it out of the ground ourselves? The U.S. has plenty of land. But the answer to that reveals the true nightmare of this supply chain crisis. It is not just about having the rocks in the ground. It's about the recipe required to refine them.
Exactly. You generally don't go out and just mine a pure scandium deposit. Scandium is primarily extracted as a byproduct of refining other things, like titanium, nickel, and uranium.
Oh, interesting.
Yeah, it's a highly complex metallurgical process called solvent extraction. You basically have to create a massive, highly toxic chemical soup, constantly tweaking the acidity and introducing highly specific chemical binding agents just to pull out trace amounts of scandium.
And China controls over 90% of the global supply of that refined scandium.
Over 90%.
The Modern War Institute points out that China kept commercial prices artificially low for years, hovering around like $640 per kilogram. By dumping it on the market at that price, they essentially made it financially impossible for anyone else in the world to justify the massive capital expense of building a competing solvent extraction refinery.
They happily took a lower profit margin for a decade to build an absolute monopoly. It was a very patient, very effective industrial policy.
And now, the West is paying the price for letting their own refining capacity die. When the U.S. Defense Logistics Agency needed to guarantee a secure, non-Chinese supply of scandium for the defense stockpile, they couldn't just go to the open market.
No, they had to pay an astronomical premium.
Yeah. The government awarded a $40 million contract to Rio Tinto to source scandium from Quebec, but that $40 million only bought them 6,384 kilograms of scandium oxide. If you do the math on that, they paid roughly $6,250 per kilogram.
Wow.
That is nearly a 900% premium over the old commercial price.
But you see, that 900% markup isn't just the cost of the raw material. The U.S. government is essentially paying for a time machine. They are funding the massive overhead required to bootstrap a lost supply chain back into existence.
Right.
And China knows the West is trying to rebuild this capacity, which is why they're now tightening their grip on the technology itself.
Yeah, this part of the geopolitical analysis is just staggering to me. In December 2023, and then again with stricter rules in October 2025, China didn't just restrict the export of rare earth minerals, they banned and restricted the export of rare earth extraction technology and equipment.
It's a huge escalation.
It means that Chinese engineers and technicians now require a government license just to travel overseas and provide basic maintenance on refining equipment.
Wait, so if they have legally locked down the tools and the engineering knowledge to process the minerals, aren't we just completely stuck? How do you build a competing extraction industry if you are literally barred from buying the instruction manual?
You do it the hard, slow way. You fund parallel supply chains from the ground up, figuring out the chemistry yourself. We see this with investments like the $400 million going into Australia's Sunrise Energy Metals to build a primary scandium mine and refinery.
But that takes years, doesn't it?
It takes years of capital investment, environmental permitting, and metallurgical trial and error. The geopolitical clock is ticking much faster than the mining development clock, which leads us to the most aggressive strategy of all. If you can't buy it and you don't have time to mine it, you have to invent an alternative. Here's where it gets really interesting, because American innovators are looking at these geopolitical choke points and deciding to just bypass the rare earth elements entirely. I was digging into the work of a company called Niron Magnetics, based in Minneapolis.
Oh, yes.
They recently received a $150 million conditional commitment from the Department of War, which was highlighted in that White House announcement. And what they're doing sounds like science fiction. They have developed the world's first high-performance, rare earth-free prominent magnet, and they're doing it using iron nitride. Specifically, a magnetic phase called alpha double prime F16N2.
The history of this material is such a great lesson in how scientific progress actually works. This specific phase of iron nitride was first discovered back in the 1950s at Cambridge University, entirely by accident during a steel hardening process.
A total accident.
They knew it had powerful magnetic properties, but nobody could figure out how to isolate it or manufacture it purely.
It remained a scientific mystery for decades. It wasn't until around 2010 that researchers at the University of Minnesota finally proved empirically that it had a giant saturation magnetization. But how does this actually work at a molecular level? Like, what makes iron nitride so special?
It is all about the crystal structure.
Yeah.
In regular iron, the magnetic fields of the atoms point in mostly the same direction, which makes it magnetic. But in this alpha double prime phase, they take nitrogen atoms and physically wedge them into the iron's crystal lattice.
Okay.
This stretches the iron structure just enough that it forces all the iron atoms into perfect, ultra-powerful magnetic alignment.
And what's crazy to me is that this breakthrough in 2010 was funded by a Department of Energy program called REACT, which was created specifically in response to the very first rare earth trade crisis with China back in 2010.
So a geopolitical crisis sparks government research funding, which solves a 60-year-old physics mystery, which results in a commercial product that solves the current geopolitical crisis.
It is a perfect loop.
It really is.
Yeah.
And the technical advantages of this material go way beyond just supply chain security. Traditional high-performance magnets, like the neodymium magnets used in electric vehicles, require the addition of heavy rare earths, like dysprosium, just to maintain their magnetism at high temperatures.
Right, because when an electric motor gets too hot, a standard neodymium magnet starts to vibrate at a molecular level, and it literally shakes its own magnetic alignment apart. It loses its power unless it has those heavy, super rare elements baked into it to act as a chemical anchor.
Exactly.
But Tom Granger, the innovator running Niron, pointed out in the interview that iron nitride has intrinsic thermal stability.
Because of how tightly those nitrogen atoms are wedged into the iron lattice, the physical structure itself locks the magnetic alignment in place. You do not need to add a chemical anchor like dysprosium. It natively resists the heat.
That is a massive engineering advantage.
It's huge.
Yeah.
But just as interesting is how they are actually building the manufacturing base for this.
Oh, I found this detail fascinating. Niron is located in Minneapolis, which happens to be a historic hub for the hard disk drive industry, places like Seagate and 3M. So there's a deep bench of material science talent there.
Sure.
But the United States essentially surrendered its commercial magnet manufacturing industry to China decades ago. To actually scale up a factory, Niron needed people who knew how to build the physical production lines. So they went out and tracked down the original founders and engineers of the U.S. magnet industry guys who were nearing retirement or had already retired.
They brought them back for one last job, almost like a heist movie.
Literally, they brought them back specifically to train this new younger generation of engineers and literally rebuild American magnetic manufacturing from the ground up.
It's a brilliant strategy for knowledge transfer, and the urgency behind it cannot be overstated. If we look at the timeline in the defense sector, integrating a new, unproven material into a military platform typically takes 10 to 15 years of rigorous testing and qualification. You just don't put a new magnet in a missile fin without a decade of data.
But because of the extreme supply chain panic, because they literally cannot guarantee they will have rare earth magnets from overseas next year, that timeline is compressing violently. Granger noted that defense customers are coming to them now demanding deployment of these iron nitride magnets in just 24 months.
That is an unheard of acceleration for defense procurement. It highlights exactly how fragile the military feels their current supply chain is. They're willing to fast-track an entirely novel material because the risk of relying on the old material is suddenly deemed an existential threat.
So what does this all mean for you listening to this right now? We've talked about billions in White House funding, F-35 fighter jets, and 60-ton global bottlenecks. But this isn't just about military hardware. This iron nitride revolution is coming directly to your driveway and your living room.
Yeah, the exact same magnetic principles that guide a missile fin are what turn the wheels in the electric vehicle you drive, or spin the fan in your home air conditioner.
Exactly. Niron is already partnering with major automotive players like Stellantis to put these rare earth-free magnets into electric vehicle traction motors. They're going into e-bikes, they're going into commercial HVAC systems, they'll soon be in a high-fidelity consumer audio speakers. And what makes adoption so viable for these companies is the form factor.
This is a crucial engineering detail. To use these new magnets, a car manufacturer doesn't have to completely redesign their entire electric motor. An electric motor generally consists of a stator, the stationary outer ring, wrapped in copper wire that creates an electromagnetic field, and a rotor, the spinning center cylinder packed with permanent magnets.
And Granger explained that the outer casing and the stator can remain exactly the same. The only thing that changes is the internal geometry of that spinning rotor. Manufacturers just have to cut slightly different slots into the steel to hold the iron nitride magnets instead of the neodymium ones. And as a massive bonus, these new iron nitride magnets are actually lighter than traditional rare earth magnets.
In industries like robotics, aerospace, and automotive design, shedding weight is the holy grail. A lighter rotor means less rotational inertia. The motor can start, stop, and change directions much faster and with less energy.
That's incredible.
It allows for incredibly precise, rapid movements in a robotic arm on an assembly line. It is a genuine performance upgrade, not just a geopolitical workaround.
And this isn't some distant, decades away pipe dream either. Niron already has a commercial pilot facility operating right now in Minneapolis. And they've broken ground on a much larger commercial plant in Sartell, Minnesota, which is expected to start shipping products at scale by late 2027. We are watching an entirely new industrial base being born in real time.
That brings us to a really vital philosophy behind all this innovation. Tom Granger used a phrase that perfectly captures the goal of this entire movement. He said the aim of these new technologies is to be essential, not exclusive.
Meaning, they don't want to just kill off the old rare earth industry and replace it entirely with iron nitride, simply creating a brand new monopoly in Minnesota.
Exactly. We don't want to trade one massive geopolitical dependency for a new one. The goal is to build a diversified multi-chemistry market. If you need ultimate raw magnetic strength packed into a tiny cold space, maybe you still use neodymium.
Right.
But if you need intense thermal stability and absolute supply chain security, you use iron nitride. Competition and diversity drive true resilience.
We have covered a massive amount of ground today. We started at the absolute macro level, looking at how the highest levels of government are treating critical minerals as national defense, pouring billions of dollars into securing supply chains and funding human capital.
We examined the extreme fragility of that system by looking at the 60-ton scandium bottleneck, where defense tech and civilian infrastructure are fighting over a microscopic supply of material entirely controlled by a geopolitical rival.
And we looked at how American ingenuity is responding, bypassing the processing choke points entirely by pulling an accidental scientific discovery from the 1950s, bringing retired experts back for one last job, and inventing a rare earth-free magnet that is going to power everything from defense drones to your next electric car.
It is a remarkable testament to human innovation when backed by necessity. But if we connect this all to the bigger picture, it leaves us with a critical question to consider. As we use this incredible ingenuity to invent alternatives like iron nitride, and as we completely restructure our global supply chains to escape our current dependencies, how do we ensure we aren't just planting the seeds for tomorrow's crisis?
That's a great point.
Are we truly solving the resource war, or are we merely moving the battle lines to a different, currently ignored part of the periodic table? What happens when the abundant materials we rely on today become the critical choke points of the next generation's technology?
It brings us right back to that skyscraper we started with. We might have figured out how to manufacture our own titanium screw, and that is a massive, hard-fought victory. But a building requires a lot more than just one screw to stay standing. The work of securing the foundation is never truly finished. Thank you for joining us on this deep dive into the hidden world of critical minerals. We will catch you next time.